So for a start, maybe you have, I don't know, questions or comments about the material we discussed last time, or something you want me to explain again, or I don't know.
I think everything was okay.
Okay. Well, so last time we had the lecture in two parts. In the first part, I showed you how to handle finite words by doing algebra, basically, and looking at words in terms of products of variables instead of just mere text. And in the second part, we saw infinite words, and I tried to convince you that it was an interesting tool, a powerful tool to model phenomena. So we took, for as an example, the Hanoi puzzle, the towers of Hanoi puzzle, and we saw how we could express a solution, more or less, as an infinite word or sequences of finite words growing longer and longer, which is essentially the same thing, actually. And today, for the first part, we're going to do something similar, but with a more general technique, so which is called symbolic dynamics. This is by no means a lecture about symbolic dynamics. We have no time, and we would need to introduce rather heavy theory. So I just want to give you a taste of what's possible and what are the main ideas of this technique. So I will be less formal. I mean, I won't try to go in the details and to make full proofs. I really want you to get the big picture and to look up the details later if you need them someday because you need to perform such tasks. So symbolic dynamics talks about dynamical systems. So first I need still to be a little technical and to explain what a dynamical system is, unless you already know maybe. No? Okay. I will take very simple version where the time is discrete. So what does it mean? I have a dynamical system for me. So I should write discrete time and blah, 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 but okay. Here it's a couple x and t, where x is a set. Intuitively, is the set of states in which your system can be. So at a given point of time, what your system could be. So this is a set of all possible states of your system. It has no reason to be finite. In full generality, suppose you're modelizing some systems in physics, for instance, some particle or something. This would be the set of all possible coordinates that would be triple of real numbers. It could be finite, but in this case, things are going to be really easy, you'll see. So X is, in general, if you want to be fully general, it's a topological space, whatever you like. So is topological space. It could be something stronger, we'll see, but okay, in general, it's a topological space. And T is a continuous function. I just write shorter like this. From X to itself. And so basically, T you should interpret as a time step. Like I'm in some state. In the next moment, since time is discrete, I can talk about the next moment. I'm sent to the new state given by t. So usually, I could give examples.
What is continuous function?
Continuous. If you really, I can write it. I just write shorter, but. Since this is why I need a topological space. I want a continuous function, and then I'm interested in the iterate. I start from some initial state x, so small x in big X, and I'm interested in the iterates. I mean the sequence given by x, t of x, t of x, and so on and so forth up to infinity. This sequence. So you could imagine, for instance, if you're more computer science oriented. X as the set of all possible states in which a computer could be, like the contents of the memory, of the processor registers, of everything. So all the possible states your hardware could be, and hopefully your hardware is deterministic. If you know completely the state of your computer at a given time, you can know the state of your computer at the next time, given by the fastest clock you can find in your hardware. And in this case, you start from some initial state, you boot your machine, and then you look at the sequence of what happens of several states like this. So that's an example. That precise example is very complicated, but it's not completely unrealistic. People doing software verification could have this point of view. And they would be interested in things like, I have some subset of configurations that are bad, like my system has a bug, or I don't know, the aircraft crashes, or we know that this thing happened, it's bad, like division by 0 or something. And we're interested in whether this trajectory, this sequence of states, at some point enters the bad state or not. So that's one kind of motivation we can have. But that's really a complicated system. So just to make something a bit simpler, a classical example on which you can say things, and that's a bit more geometric, so it has less practical immediate applications, but we can do more things in 1 hour, is the following one. So a classical example with which we will do things. You take X, the circle of center 0, 0, so the origin, and of perimeter 1. So you take the radius such that the length of your circle is exactly 1. This is just to make things easier to compute. You could take any circle. And T, a rotation around center the same, 0, 0, and some angle alpha, say rational. Like this. So the advantage of this example is that we can say many things about it. So what can I give you? A circle. We believe it's a circle. Yes. You start, say, from here, and then you rotate of some angle. So I take it irrational to make things interesting. And actually, you have many systems. If you do discrete math, there are many systems that you can reduce to this one. And this is why it's also important. It's a classical example, not only because we can say many things about it, but also because we can reduce many systems to it. But OK, another example that also will be interesting for us at some point. So another example.
Is it true that in this example the set, the sequence, and the set from the sequence is dense?
Yes, that's actually one of the things you can say. For any starting point, the sequences are dense in a very strong meaning. They are uniformly dense, if you wish. So yes, that's one of the things we can say, and we will see how to actually not exactly prove it, but directions about how to prove it a little bit, or to make this intuition a bit more formal. And for this, we're going to use infinite words, actually. That's exactly the kind of questions we will be interested in. But I need another example, because I haven't told about infinite words yet. And actually, with the infinite words, you can make the simplest system you could imagine. So I will call it, I don't know, YX, another system. YS, sorry. Where Y is, some set of infinite words. And S is the simplest operation you could imagine. It's an operation, you start from an infinite word, you remove the first letter, and that's it. So S of some word W is equal to W prime, say, such that W prime of N is equal to Wn plus 1. So now I gave you 2 examples of dynamical systems. Here, by some set of infinite words, I mean you could take the set of all infinite words over some alphabet, for instance. I need that this set is invariant by this operation. This operation I call the shift, by the way. S is for shift. So this is the shift. so I need a set that is shift invariant, say. If I take the shift of an element, I need to still be in my dynamical system. And I also need to give you a topology. Like I required that my set is a topological space, because otherwise it's really, if you take completely arbitrary set without any information, it's really difficult to say anything about it. So at the very least, we want it to be a topological space, and we want the shift to be continuous for this topology. And we have another motivation to give a topology on a set of infinite words. You remember last time I told you, like, if you have sequences of finite words that grow longer and longer and that are prefixes of each other, then somehow this converges to an infinite word. And I told you, for now, we'll just do it like this, but there is a way to give a formal meaning to this limit, to take the limit of a sequence of words. So here we're going to do it for infinite word. If we have a sequence of infinite words, the topology will give a meaning to the limit of such a sequence. Hello? So what could be the topology? Actually, the simplest way to give a topology is just to give a distance. Like I have two words. The notation will clash a little bit, but I have two words, infinite W and W prime. Probably it's the limit of having distance for its prefixes. The thing with that is it's not quite a distance, because if you have only finitely many bits that differ, the distance will be 0, but the words will be different. So if you really, that's actually not distance, that's a pseudo distance, I guess. Like you don't have that points at distance 0 are exactly the same. But something along these lines. Actually, something that looks like what you suggest, but that solves the problem I just mentioned, is to take this. Yes? Series, what do you mean series? There are many things you can do with series.
Yeah, we can take as indicators indicators as the coefficients of series and I don't know, some geometric progression.
Right. Okay, we could do this. I suggest something even just simpler, because the advantage of this is that you can take completely dumb definition, it will work. So I won't give up this. So I say that the distance between two words, I can define it as 2 to the minus n, where n is the, let me write this properly. Yes, the minimum of this set. So the smallest integer such that we have a difference. So you look at your infinite words, you start from the beginning, and as long as they are the same, you continue to advance, and when you find the first difference, the first index where there is a difference, you call that n, and your distance is 2 to the power minus n. So, and of course, if you have no difference, this will grow to infinity, so you set the convention that the distance is 0. It is symmetric, for obvious reason, and you can check that it satisfies the triangle inequality. So just, I can erase the definition on the top. So the idea is that distance, if two words have a very long common prefix, they are going to be close. And what happens after the common prefix is actually neglectable, that's the way we do it. So, for instance, I think you get it, but and so on. Here you count. I start to count from 0. So if the first letter would be different, they would be the words would be at distance 1, and this is the biggest distance you can have. And here 0, 1, 2, 3, 4, 5, 6. So the distance between these two would be something like to the minus 6, 1 over 64. And so, okay. And we can check that the shift is continuous That's also a reason to use this distance about the first, locating the first difference and then taking some decreasing function. It would work with any sufficiently decreasing function, by the way. The shift is continuous. You can see that. Like if I start from two words that are close, I remove the first letter of both, I still have something reasonably close. Yeah, okay. That's a meditation, and then you can see it like this. The worst that could happen is that if you shift, the worst that happens is that you get the first difference closer to the origin by one index. It could happen something else could happen. You could have the first difference here, and so if you take the shift, you could even have two closer words because you remove a difference. But the worst that could happen is that you have this difference here, and then you make it here, so you double the distance between the words. So if you have two words and you shift them, you can never be more than this. And then by classical results of general topology and metric spaces, you can deduce that your function is continuous. It doesn't make point go too far apart. So that's very nice and everything. Now we have two dynamical systems. We understand a little bit how they work. Yes, for this, obviously, the topology is the usual thing on the real line quotiented by the integers. Like we identified this circle with the interval 0, 1, and we work modulo 1, and so we have the classical topology over the real numbers, and everything works, the rotation is continuous. So usually when you're doing theory like this, you start by giving a definition, then you give a couple of examples, so far so good, and you want interaction. Like you have two dynamical systems and you want a relation between them. If you do topology, you have, for instance, continuous function. They send a topological space to another topological space by preserving topological properties. And here we want something similar for dynamical system. That's the next classical step. We want to define some map that sends a system to another by preserving both the topology, so probably this map is going to be continuous, and the dynamical properties of this map. So for this, in full generality, if I have two systems, xt and ys, oops, sorry. A function from x to y, which is continuous. This is a way to delegate. Usually you know something more about x and y. Here I'm extremely abstract, but usually when you have concrete examples, you know tons of things. So the function being continuous means essentially that the function is not too ugly with respect of what you know about the problem, because you can choose the topology. So f is continuous, it means f is reasonable in some sense. And about the dynamics, we want f to be equal. So the idea is that whether I make a step of my dynamical system and then take f, or take f and then make a step to my dynamical system will be the same. I think I can even draw a picture. Like you have your system x, you have your system y. You can walk one step in x, or you can take f to arrive in y, and you can take a step in y, and here the diagram commutes. We say like you can either take the step and travel, or travel and then take the step, and you will get the same results. So you have kind of a mirror. The behaviors here and here are a bit of the same.
So it's kind of morphism.
Yes, it's a kind of morphism. We call that a conjugacy. So implies a semi-conjugacy excuse me. F is a semi-conjugacy. Why semi? Somebody can guess?
One direction?
Yes. If you want both direction, if f is a homeomorphism, like a bijection that's continuous in both ways, and we have f minus 1 semi-conjugacies, then we call that f is a conjugacy. And I won't get into the details of that, but conjugacies preserve all good dynamical properties, like I explained for continuous functions preserve things in topology, well, linear maps preserve things in linear algebra, well, here conjugacies preserve properties of dynamical system. So I won't make this formal for now, but now you can see a plan. So the idea of symbolic dynamics is as follows. You have a very complicated system, like something, even this, okay, if we know nothing about this could be complicated. And we want to say things about it anyway. So one way to do it is to find a conjugacy, maybe of your system, maybe of a subsystem, we don't know, but you find a conjugacy between your system and something like this. Something that's just a set of infinite words and the shift map that eats a letter at the beginning. And here you can use all that you know or that we will learn about infinite words to prove things about your system, because this action of eating the first letter is really simple, about dynamics, I mean. You can interpret all definition, all concepts of dynamical system, things about, I don't know, being dense or trajectory, all that you could imagine about dynamical system, you can interpret it in this very specific system where it becomes a natural definition about words, then you can work about words and prove things, and hopefully conjugacies preserving what you just proved on your set of words, you will get it on your initial system. And so that's what I want to do today in a very rough way. I want to take this system of rotating circle with an irrational angle, send that to a specific set of infinite words, and show things on these words that will teach us, that will give us information about the initial system. I won't make everything formal, but that's the idea. Map circle to words, prove things are words, and see what happens on the circle initially. Sounds good? So just historical notes. This is not exactly the first example. This is almost the first example of such a procedure. A keyword that I didn't say yet and that I should say somewhere is Sturmian word. So I won't go into details because otherwise I would just make 5 hours lectures about exactly this, and this would be even more boring. The idea is that this is one of the first examples of infinite words that has been studied as an infinite word. I mean, not an object that came from another domain, but something that were just an infinite word and that we studied as an infinite word. And they are essentially a generalization of what we're going to say now. You can imagine them as codings of rotations like this. And you find them everywhere. They are a bit ubiquitous objects. A bit like pi. The number pi pops up a bit of everywhere, even if you do things that have nothing to do with geometry. Sometimes you see pi in your calculation. In discrete math, and if you try to get close to words with your problem, to study your problem with words, very often you will see Sturmian words popping up. They have lots of equivalent definitions. I will say more about them later, but just to tell you, this is a keyword if you want to look it up. If you want to get more information and you want to look for books or whatever, this is what you should ask to your favorite search engine. And so, yes, this is basically the second historical example, the first one being a bit too abstract for us now. Okay, so I will ask a question about this circle. Erase this. I will pick a very specific example. It's not that useful, but just to fix the idea, I will take rotation of angle exactly alpha equals phi minus 1, where phi is the golden ratio. So if I expand it, this becomes this, etc. So okay, why not? You could do it with your favorite angle. So by the way, I insisted a bit on the angle to be irrational. I told you I take alpha irrational a couple of times. Can you tell me why? What happens if I take alpha not irrational?
We can take
it's periodic.
Yes, it's going to be periodic. Because the denominator, the bottom part of the fraction will be the same, and since we're working modulus something, you have only finitely many possibilities for the top part of the fraction, so at some point it will repeat. This is why I want it to be rational. If alpha is rational, you get a periodic system that just hits discrete points, always the same, and the words you would get would be periodic words, and we wouldn't have much to say. So okay, take an irrational angle, say this one, and the question I want to ask is something like, I will define an interval, I will split the circle in two parts. So this part is going to be part of size alpha, and this part is going to be of size 1 minus alpha. And we can even give them names. So for names, I will be very original. I will use bits. Like this is part I call 0, and this part I call 1. Why not? And the kind of question I'm interested in is if I start from a point, x, and I look at the trajectory of x, or the orbit of x. So the orbit of x is exactly what I draw here. I forgot to tell definition. Orbit is exactly the sequence x, g of x, g square of x, and so on. So, no, something's unclear?
Alpha is greater than half of the...
Yes, sorry.
Oh.
Yes, my bad. You're right. Like this. Yes. The point is that, yes, you take your angle alpha and you split after alpha, so it's like this. It would just reverse the zeros and the 1, and it wouldn't change much of what I'm going to say, but okay, let's make this precise. And now the question is, if I start from some initial point x, what is the average time that I spent in each interval? Like it's stronger than just being dense. It's like on the average, how long do I spend in interval 0 and how do I spend in interval 1? I know that these are very bad names for intervals, but it will be, we will have a reason for this. So can you make a, is that clear, or should I define it a bit more precisely?
It's clear.
Okay, can you make a guess then? If I start from a point, you can even start from this point if it helps you, and on the average, what's the percentage of time that I spend in interval 0 and what's the percentage of time I spend in interval 1?
Alpha is 1.
Yes, okay. So we can guess here that on the average we will spend alpha percent, well, 100 alpha percent of time here and 1 minus alpha here. But if you say that, just because you guessed that, it means that you assumed something about the rotation. Because you can only say this if you think that the rotation is somewhat very uniform, like it always moves at the same speed in some sense. And so this, we can make this formal. I won't, but you have things. So here the keyword would be ergodic theory. So once again, I won't go into this, but just in case you want to look it up. Ergodic theory is the theory interested exactly in this question. Computing the proportion of time I spend in which subset of my system. And okay, this seems like an abstract question, but you have many situations where it makes sense. Once again, I'm working on a circle, but if you're working on some computing system, whatever it is, you might be interested in the proportion of time in which your system is in a critical state. What I mean by critical state is that if you remove the electric power, then something bad happens. You know, when you update your Windows machine, you have please don't remove electricity, I'm updating the system. So this could be considered a critical part of a critical moment in your system. And so you want this to be as small as possible. And in the first place, you need to compute it. So that's kind of thing that you could ask. So that's much stronger than just being dense. It's about being dense uniformly, like moving at the same speed all the time. And so we can kind of prove it in a simpler way. Something I should mention, though, is that you cannot do that with only topology. Here I started to lie already, and not mentioning that I lie, because I told about the length of these intervals. So if you really want to make everything precise, you need measure theory. You need a way to say, because here on the circle it's simple, the size of an interval, everybody sees what it is. If I give you a set of infinite words and a subset, what is the size of the subset? You see what I mean? Here it's obvious that we have something of size alpha and of size 1 minus alpha. But now if I give you the set of infinite words and something here, what will be the size of this? In full generality, it's difficult to say. So we would need more advanced tool to talk about this, so I will skip it. But if you want to prove things formally, you will need more tools. Okay, so enough warnings. How do we do this? Do you have, I don't know, a guess about what I'm about to do now? I want to send this system into some. So I have this, and okay, I will even change the name. I can call that the circle and the rotation of angle alpha, and I want to send this on infinite words, or maybe a subset of this, but infinite words, and the shift that eats a letter. So if you forget about the dynamics for a second, how could I do this? How could I code points of my circle into infinite words?
And what is alphabet sigma?
Okay, it could be whatever alphabet you need. You can choose the alphabet, as long as it's finite. The alphabet I have in mind is 0, 1, if you really have to know.
We can quote numbers between 0 and 1 by, so the number is, here is like a fraction.
Yes, sure. Yeah, it is between 0 and 1, yes.
1 and when we shift, we just...
So, okay, just, you want to say that I write the number in binary, like it's 0 point and then it's infinitely many bits, and so you can take all that's after 0 point and this is infinite word? Do I get that right?
Probably.
Okay. We could, but then, as you felt, so this, given the question that I asked, this is a valid answer. Here, I might need to do something different because, as you felt, this won't interact well with the shift because we have no reason of, well, it will do something, but something that's not exactly interesting.
Given a point x, we just apply rotation many times and then get a sequence of 0 and 1s based on the parts of a circle.
Okay.
Let's assume this the Commission infinite words.
Everybody got that?
Yep.
Oh, you're frowning. No, okay. I will just repeat it because I'm not sure we can hear you in the microphone. So what he said is that if we start from some point x, then we can apply the rotation infinitely many times. So actually we're looking at this sequence, if we're making it a rotation. We apply the rotation infinitely many times, and each time we remember whether we are in part 0 or in part 1. So I should give a name to this. So actually we have a partition of our circle, and in full generality, if you want to do this with something else than a circle, you need to partition your set of states into finitely many pieces. So I have a partition P, so P of x equals 0 if and 1 if. So this is the partition, so the formal version of what I drew on the board. And then the coding would be something like this. If you start from x, then you code P of x, P of the rotation of x, p of twice the rotation of x, and so on and so forth. And this is an infinite word. Or in other words, let me be consistent with my notation. Yes, call that. So now the rotation is called r and the shift is called s. So the letter t that I used here is free. I will use it to denote the trajectory. So it is something else. So t of x is equal to some word infinite w, such that wn is p of x. So I wrote this that way because then you can check that it commutes with the actions. I mean, eating the first letter is exactly the same as moving one step forward in a circle. And so if you write it formally, you can check that this commutes with the action. Whether you first move and then code this as an infinite word, or code it and then remove the first letter, will give the same result. So now we have what I announced. We have a conjugacy. We have two dynamical systems like this. We check that this is continuous. This is continuous. We have something, or we should check that this is continuous, but okay. Trust me for this. And you should just write it down. It's nothing difficult, just a bit long. And that commutes with the actions. Okay. One thing that we have a small problem here. Small problem is we cannot reach all the infinite words. Like, we have no reasons for this to be a bijection, because here we won't reach all the infinite words. We will reach only a subset of the infinite words.
Only with the fraction of zeros, with the constant fraction.
Okay, so yes, I see what you mean. That's true. That's actually quite true.
The limit of this fraction.
Yeah, sure. Okay. Something a bit more simple. Just to say, whoops. If I just want to say, I don't reach all the infinite words. Just show me one word that is never reached. Not with fractions. Something very simple.
Constant zero.
Yes, actually constant whatever. Yeah. And stronger than this, any word that has two ones in a sequence has no chance to be a trajectory. Like, if you have 1, 1 somewhere, this means that you would spend 2 steps in a row in this interval, and this interval is smaller than alpha. So you have no chance, and you cannot, if you're here, you have no chance to skip the whole zero part. So you cannot be 2 steps in a row in the part number 1. And for the same kind of reason, you cannot be 3 steps in a row in the part 0. Because you will reach the part 1 at some point. So, and actually I'm glad you got this intuition, because maybe this one will work better. Where is it? Not much, okay. So here I will call this set F for now, because I don't know what it is. So here it's not exactly sigma, it's F. And F is not equal to sigma to the n, because W in F implies 0, 0, 0, not factor. And 1, 1, not factor of W. So here I want to stop to make a couple of comments. First, you talked about the fraction. Actually, the usual term for this is frequency. We want to compute the frequencies of letters, and say that that's what you call a fraction, actually. If you have a word with, on the average, 1/2 of zeros and 1/2 of 1, we say the frequency of 0 is 1/2, and the frequency of 1 is 1/2. But you could imagine words with the right frequency that still has problems. For instance, I could start with 0, 0, 0, and then make something that is exactly with the right frequency. And since you took a limit, it's not important what the 3 first bits are, and then you would have a problem. So actually, your condition is not sufficient, but it's necessary. We will need to have the right frequency, but we need something more. We need this. So that's the first comment. And actually, frequencies of letters are something classical. I will show you, we will compute the frequencies of letters in this set with a standard technique. And that's something well known. That's something we give as an exercise in lectures and so on. So if you reduce your problem to something like compute the frequencies of letters, usually you're happy. This is the simplest case of ergodic theory, actually. If you think about it, the frequency of a letter is just, on the average, the time you spend with the first letter of the word being this. The frequency of alpha is already taken. I have some letter L, and I have some infinite word. The frequency of L in this word, you can see it, can be seen as the average time we spend with the first letter being equal to L. Because I recall you, the action is a shift. We eat the first letter. So we look at whether the first letter is L or not. Then we remove the first letter. Then we remove the first letter. And each step, we remove the first letter and we'll look whether the first letter is or not L. So we have a partition of words, which is the word starting with L and the word starting with something else. And we have an action that eats the first letter. And your frequency is actually just, it is the same question as this. It's the proportion of time we spent with the first letter being L. But okay, never mind. It's not the main point. Second point, something else, is that here we could consider a set. It's not exactly the case, but we have a set that is defined by forbidden factors. No, nothing's bad. We could consider the set of all words that have no 0, 0, 0 as a factor and no 1, 1 as a factor. It's not exactly F, it's something else, but we have a huge theory about this. If you get a set of infinite words that is defined only in terms of forbidden factors like this, then it's the same. You have lots of tools that you can look up and work about it. So once again, I would need a full semester if I wanted to explain everything. But just to mention you that if someday you end up having something you modelized and with a set only defined in terms of forbidden factors, there are many, many things you can do with their connection with automata and so on.
Can we have 2 zeros in a row?
I think yes. That's a good question.
But how?
You start here, and then you probably will jump here.
Yeah.
Yes, it's not obvious, but it's clear that you won't get something periodic like 0, 1, 0, 1, 0, 1, 0, 1. But it's not clear to see how you can have 2 zeros in a row. And actually, yes, you have to start very close here, and then you will skip it altogether. So yeah, I give you another keyword, subshift. A subshift is a set of infinite words defined in terms of forbidden factors, exactly like this. So if you're interested in one of these subjects, I can give more lectures about them, of course, but given the death rate of students from lecture to another, I'm not sure it will be useful, so you have to tell me. I can teach more about any of these subjects later. So back to the problem. We have a code of any real number. We should ensure something. We forgot something. Sorry. So we have a code. We start from a real number x, and then we have this that gives us an infinite word. All right. I told you, okay, this map T is continuous. Don't worry about it. There is something else we should worry about. It's good that it's continuous, but we need something else if we want to do business. You should be sure that it's injective. Like, we have no reason for now. Actually, it's true, but you should make sure that if you start from 2 different real numbers, you will get 2 different infinite words. Do I make sense? Yeah. Because otherwise, maybe, and this is exactly where we could have problems, because if we have many points mapped into a single infinite word, then our counting will have problems. Like we have no reasons for things to be preserved, especially the sizes of the intervals have no reasons to be preserved. So I won't do it, but to show that it is injective, you actually start from 2 points that are close, say, and you rotate them around the circle, and at some point you show that you will get this situation. So here you need some kind of density, but in a weaker sense. You just need to know that an irrational rotation meets every closed interval, say, non-empty open interval, it's the same here. And that's a result you can show by elementary means. And so if you have 2 points that are not the same, after maybe a very long time, you will get this. And so you will have a bit of difference and the words won't be the same. And you can even show that the closest the points, the longer it takes to have a difference. And what is that exactly?
What's the question?
Okay. I can show formally that if I take 2 points very close, then it takes a very long time to rotate them until this situation where they are separated. And actually, the closer the points, the longer it takes to get an error. This has a name, formally. The property I just explained is called something that you know. It's continuity. Remember, the distance between two infinite words is basically inversely proportional to the index of the first difference. So what I said is, if you have the closer the points, the longer you have to wait to find a difference. So I just said, the longer the points, the closer will be the trajectories, because you will have to wait longer to find the first difference, and with the distance we defined, it means that the words will be very close. So if we have very close real numbers here and we code them, we will get words that are also very close according to the distance we used. That's another advantage of the distance we had. And if you make it up with the right quantifiers at the right place, it becomes continuity. I'm telling you that because if you try to open a book on this subject, you're going to face very abstract theory where you have topological space and continuous mappings all the time, and okay, things are continuous and so on, but it's purely abstract. Like, okay, you should, they show things about function being continuous and so on and so forth, and I want to show you that this actually has a meaning that we can understand very intuitively when we have things. This is why we want things to be continuous everywhere. Okay, so end of the parenthesis. So now we have an idea about f. We said f has these forbidden factors, so the words in f cannot have these factors. We explained somehow that the words in f must have some frequencies for the letters, frequency alpha and 1 minus alpha. But okay, what is f exactly is not clear yet. So what about we compute one trajectory, like we pick an x somewhere, and we try to give an explicit formula for the word. So I have some real number x. Can we try to compute t of x? So I mean, like I give you give a formula that yields the nth bit of this word. This is an infinite word that we define like this, which is the coding we are talking about since a few minutes already. Can we give a formula for this infinite word? Like, what is the nth bit?
Yes, here it's written.
Okay, we have a formula like this. Here, I want to expand this then. Because if I want to compute it, say I could take a computer and compute the nth iterate of the rotation, but I want to write it a bit more explicitly. Okay. First of all, before writing this, what would be the nth rotated of x explicitly?
floor of n times alpha.
Plus alpha.
Plus alpha, maybe. No, I think it's like this. I think it's n alpha. Okay, we have n alpha, that's for sure. Because if n equals 0, then we do nothing and we get x. So x plus.
Plus x.
Okay, I will write it here. But yes, you're right. X plus. And then we work modulus 1.
Floor.
Yes. No. Here, excuse me. I'm not talking about. I'm talking about real numbers. I'm not in the symbols yet. I just want to know where am I on the circle. I want a real number. Like, I'm just asking if I take x and I rotate n times, what is the new x?
Oh.
Yes.
Right.
So it's just so it is a fraction.
Yeah.
I could write it like this. I know it's not an integer, but you see what I mean. You drop the integer part. Cool. And now the question is, so we're happy we have this. And now the question is, if I have this formula, okay, why not? How can I compute exactly this? Like, how can I know, how can I write that whether we are in this part or in this part? So of course we could write it with like this, like we can if blah and so on. But here I'm trying to find some formula that is fully explicit, just pure arithmetic. And your idea is actually has something to do with it. Don't drop your idea. Here you might need it. By the way, you should tell me when is the break exactly, because I'm not used of the exact. I mean, please interrupt me if I'm being.
In 20 minutes.
Okay, perfect. We'll be in time. So sorry, you were trying to discuss something?
Just explain the question.
Okay. All right. So here we have a number x plus n times alpha. And we said that if we want to rotate on the circle, we should take modulus 1. We should drop the integer part. Why not? But this integer part that we drop, it has an interpretation. What is it? Exactly the integer part of x plus n times alpha is what? Suppose you start with something between 0 and 1. We have 0 point blah, 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 something. So this is a real number between 0 and 1. And now we compute x plus n times alpha. So we obtain something. The fraction part, everything that's after the decimal point, is where you are on the circle. But the integer part is what?
How many times have you done a full circle?
Yes, the number of turns you've made like this. So now we want to understand whether we are here or there, like in part number 0 or in part number 1. In part number 1, almost by definition, if you are in part number 1 and you may take one step, in the future we'll have completed a turn. Like, it's exactly why I chose this length of interval, because starting from here, if I rotate once, my future self will have one more turn, because I crossed the boundary here. And so by combining this idea with this idea of what is the integer part that you mentioned, so you got the integer part and you got the interpretation of the integer part, I can write this. So this is the number of turns that future me will, in one step, will have taken, and this is the number of turns that I have taken. And this is what, now you understand why I named this 0 and I've named this 1, because otherwise you need to recode everything. But here I have an explicit formula that is, I think, a bit easier to manipulate than this, and that gives me the nth bit of a trajectory. That might be useful if you want to prove that they are injective, typically. Yes?
But if I'm farther than half of but in part 0.
If I'm here, say I'm here, I will end up here, and they have taken the same number of turns. Say this is, I don't know, 4 point blah blah blah. This will be 4 point another blah blah blah. If I want to go to 5 point, I need to cross this boundary here.
If we add alpha,
yes.
It's more than half of the circle.
It's more than 1/2 of the circle. I think you're right. The computation here is, we can try to calculate it actually. Because here, if I have x less than 1 minus alpha, it implies that x plus alpha will be less than 1. Just you add alpha on each side of the equation. And here is the point 0, which is also the point 1. So yes, geometrically it's not obvious. Like, I think that's because we, yes?
We have x less than alpha, not 1 minus alpha. 1 minus alpha is the length of the segment.
Yes?
And the point between two
yes.
zones is alpha.
Yes, I think that actually we got this back first because you remember at the beginning we swapped alpha and 1 minus alpha. And I think this is where the problem comes from. Because here, what I wrote initially was something like this. My picture is wrong. That's the bottom line, actually. My picture is wrong. I wrote something like this. So I should make another picture, of course. And here it makes sense because the size of the rotation is exactly the size of the interval. So actually, it's just my picture being wrong. If you want to do the picture properly, you should start all over again. But the idea is that the size of this interval is exactly the size of the rotation. So you can see it by swapping what is red and what is black. It makes sense here? Yes. Okay. So yes, we had a small accident with the picture at the beginning, so this is why.
So could you draw a
I'm bad at drawing picture actually. In full generality, here we took a very specific alpha, but actually you can forget about this for a moment.
It depends whether it's
yes, I know. Yes. So just to make things simple, take something that is less than 1/2.
No, I understand
yes.
how it looks like. I just want to see it on the board.
Yes, I see. But I will take. I can show you on the board with an arbitrary angle and not specifically with this one.
Yeah.
Okay.
But we need to know whether it's less than 1.
Yes, that's what I want to make the picture with the explicit picture with angle less than alpha, because like this it works better. Otherwise, yes, you have coding complication. So if your angle is less than alpha, we will even take a rational angle just because something like 1/4. So this is 1/4 plus a very small irrational epsilon, which is exactly the width of this side, for instance. And now, so this is your interval named 1. This is your interval named 0. And the rotation is exactly the same. It's 1/4 plus epsilon. So this means that I sent this point on this point, this point on this point, this point on this point, this on, let's say, here with a very small difference, and so on and so forth. And so now, since the rotation is exactly the length of the interval, the only way to take a new turn here is to be in the interval. I mean, the first point being in a new turn is exactly this one. That's what I explained. Okay. So you like this picture better? Okay. And I chose exactly this example. I shouldn't have because you're right, actually. That's something I tried to hide from you to make things easier. But if you have an angle more than 1/2, you have to work a little bit more to make the formula correct. So what you can do is you can take 1 minus this angle, and you will get essentially the same things. You just swap 0 and 1s. I mean, yes. Yes, exactly. Up to, so, okay. But I think with 1/4 it's easier to understand. So okay. I chose exactly this number for a reason. So I will explain one more things on this picture, and then I will skip a bit of the rest. Okay, so we have these infinite words, which are actually one possible definition for the Sturmian words. I left this thing here. You can define Sturmian words exactly as a word is Sturmian if you can obtain it with this formula for a fixed x and a fixed alpha. So this is the definition of Sturmian words. And all of them so code different trajectories of rotations. Okay. And I want...
So Sturmian words are the whole image of the circle or what?
A Sturmian word is the trajectory. If you take a rotation with an irrational angle and you take a starting point x, then a Sturmian word is going to be the coding of the rotation, exactly like we've been doing, like 0, 0, 1, 0, you do. And all the words that you obtain, it's an if and only if. A word is Sturmian if and only if you can write it, if and only if there exists an x and there exists a rotation such that it can be written like this.
Set F is Sturmian words.
Actually, it's a subset of the Sturmian words here. Because it's for arbitrary alpha. A Sturmian word could have any alpha, and here I have taken a very irrational, but even. All the f's have this angle. A Sturmian word could have any angle. This is just like this. I'm just giving you a keyword in case you meet them, because this formula tends to pop if you modelize some kind of problem sometimes. So I just want you have the keyword so you can Google it if you meet it.
The union of f's for different alphas.
Exactly. And yes, basically. So here I'm interested in this guy with a specific alpha. But it's just a side note. I'm mentioning the word really so you can Google it if you meet it. It's not exactly the main point. What I want to do here, so let's do with this picture, is something else. Okay. So the twist, the scenaristic twist of this lecture is that actually, if I write exactly t of 0, so I start from the easiest point you can find, what you have is the Fibonacci word that we saw last time. Plot twist. So I recall you, f0 is defined by a, f1 is defined by a, b, and fn plus 2 is defined by fn plus 1, fn. And this, the Fibonacci word is the limit of this. We mentioned this example of an infinite word last time, and it turns out that it is exactly the coding of rotation if you start with this angle. This is why I chose exactly this angle, and you start at point 0. I will not prove it because I want to get to the end of my lecture. But just to give you an idea, if you want to go into this, you have to notice that there is a correspondence between prefixes and intervals. Like all the guys here in 0 are guys that start, whose trajectory, whose coding start with a 0. Just because you start here and this is the first letter you have. All the guys here are the guys that start, whose coding starts with a 1. And now you can ask yourself, what are the codings of guys starting with 0, 1, for instance? And this is exactly the guys that are here. Like, they have 0, they will be sent to 1. All these guys have 0 and will be sent to 0, and all these guys will have a 1 and will be sent to 1, 0. So now you can split it more. You can say this is 0, 0, this is 0, 1, and this is 1, 0. And you can continue. You can iterate this process and get longer and longer prefixes by splitting in smaller and smaller intervals. You can have explicit formulae for exactly the bounds of this interval. Realize that thanks to the Fibonacci number here, you will get lengths that are, I recall you that these lengths are the lengths of the Fibonacci sequence. You will end up finding this. I do not want to go into here, but that's the way. And so in the end, You will also realize in the process that all the words have the same frequency. That's something we already have in our intuition. Whatever my starting point, I will have the same frequencies of 0 and the same frequency of 1. So if we have, I don't know, we have 5 minutes or not?
Yes.
Yes? Okay.
Exactly.
Perfect. What I want to do for the last 5 minutes is to compute the frequencies of, well, here A is 0 and B is 1. I want to compute the frequencies of A in the Fibonacci word. And if you did all the technical work that I skipped because I just wanted to stay at an intuitive level, you would be convinced that this frequency is exactly what I claimed to be the frequency, like the proportion of time we spend in this part of the circle. Yes, we did a lot of digression, but basically we mapped a rotation of the circle into a set of infinite words. We got convinced that all these infinite words have the same frequencies of letters, that this frequency is equal to the proportion of time you spend in each interval. So now what we can do is to pick one of these trajectories, because they all have the same frequency, so let's pick the easiest one. We could convince ourselves that it is the Fibonacci word, so now all we have to do is to compute the frequencies of A's and B's in the Fibonacci word. Do I make sense, or I completely lost everybody? Because okay. And so at last, I've reduced my problem about rotations and numbers and modulus 1 and so on to a problem about an infinite word.
But can we just say that we have 3 parts and we spend the same time proportional of each length there?
You could, but you need to show it. And the way I know to show it is actually to show it on to show this property on the set F, because that's a very strong property. Here, you feel it and it's obvious. But for a very general dynamical system, you have no reason for this to be true. I'll give you an example. Dynamical system where everybody is sent to a single point. Then the proportion of time you spend here will be 0. It has no reason to be proportional to the size of this set. So the property that you have a property that the proportion of time is equal to the size of the set. This is called the ergodic hypothesis, and there is a whole theory, ergodic theory, whose whole purpose is to give conditions for this to be true. If you open an ergodic theory book, you will have dozens of theorems telling you if your dynamical system is this and this and that, then the proportion of time is equal to the proportion of the set. But it should be proven. Here it's not true, and there are many systems where it's not true. And so if you want to prove it, the way I know, there are other ways, of course, but there are direct way. But since this is my field, the way I like to do it is to map this to the set F and then prove the equivalent property for the set F and the dynamics where you eat a letter. And since this is strictly more than general than doing it on this specific example, I do it on specific example to try to make things more explicit.
So we believe that for all words in F, a fraction of, or a frequency of ones is constant?
That I skip. I will even just make that it exists and that it has a value.
And the same for all words?
Actually, I skip the part that it's the same for all words. I will do it for the Fibonacci word, which is t of 0, and then you should use, if you want to do it completely, okay.
I can't understand, so why do we compute this fraction only for one word?
I skipped the proof that the fraction will be the same for all tx's.
So
yes, okay.
I remember
and
that you skipped, and I want to...
You want an idea of how it's
no,
true?
Not idea, just precise claim.
The frequency of A in t of x is equal to the frequency of A in t of y, t being exactly the coding of this rotation, for all x, y in 0, 1. With the same alpha, yes, yes. Here t depends on alpha, and we have the same alpha. Like with the same circle, the same thing, the only thing that changes is your starting point. And if you really want to get it, the idea is that no matter where you start, here, you will get the same frequency. And to see it, you should once again use the intervals that I shown you. Like when I tell you that you can split into intervals with code 0, 0, 0, 1, and so forth, you can see that wherever you start from, you will get the same intervals, and you can get convinced that these intervals are the only thing that matter for the frequency. I know I skip a lot of things because I want just to get one example. If I had to do the whole theory for this, I would need a few weeks just for this, and I think it's not worth doing the whole theory. So yes, I understand I'm skipping lots of things, but in 1 hour and a half, I'm doing my best to still give you an idea.
Just, I wanted
yeah, sure, but does that answer the question?
Yeah.
Okay. And very quickly, and then we'll duplicate spheres after the break. So you remember from last time I gave you a morphism. And I told you that the Fibonacci word is the fixed point of that morphism. Which means in particular that f is equal to f of, mu of f. If you have a finite word u, I will call the paric vector of u, so p of u, is the number of letters a in u and the number of letter b in u. So this is new notation. This is not the length of u, this is the number of a's in u. We call that the length in a of u, so this is why we have this strange notation. And the paric vector is just the number, not the frequency, the actual number of occurrences of a and occurrences of b. So this sums to the length of u, right? We can use this morphism, so I will write a matrix, M, that depends on u. That's like this. So if I want to save some time, I can copy. So I give you the general form, and then I explain why I write exactly this. This is an index. And here it's precisely equals to this, if I'm not mistaken. Okay. So why could this matrix be interesting? This is why I gave you the explicit form here.
It powers into Fibonacci numbers.
Okay, we have a link with Fibonacci number because we are talking about the Fibonacci. Okay, and just if you forget we're in the Fibonacci word, this matrix for an arbitrary mu, say, just for a second, take an arbitrary mu. What could we say about this matrix? I gave you a vector, I gave you a matrix. There is something to try. Like if you compute, say you have some word u, you have this morphism. If you compute this times, can you make a guess what this could be? So I have a word, I count the letters, the A's and B's, I make a vector, and I multiply by this. If I have, let's say I have 3 A's in my U, I take the, I can tell you.
P of mu of
Yes.
u.
P of mu of u. If I have 3 A's in this word, when I will multiply by this matrix, I will have 3 times the number of A's here and 3 times the number of B's here, and that will give me the new number of A and B. And of course, if I have 2 B's, says, then this will multiply here. We have 2 B's, they will give this 2 times this number of A's and 2 times this number of B's. So in general, we have this. And now, what we want to compute in this precise case for the frequency is something that looks like, if such a limit exists, let's say, so times. I start with the letter A, so I have 1A and 0B, and I want to normalize this by the 1 norm. So, of course, there is a power n here. So, if you just look at the top part here, the numerator, this is the number of A's and B's in the nth Fibonacci. We saw the equivalence between taking the image by mu and taking the next f last time. So if you take the image by mu, you take it's equivalent to taking the next fn.
It's exactly the proportion of the circle.
Yes. Yes. Actually, this is not. Yes, this is a vector. So you have two numbers here, and here I don't normalize by the usual norm. I normalize by the one norm to have exactly the proportions. Like this is exactly the sum of these two. So okay. Does that ring a bell? Like this limit exactly of this, and with does like look like something you know, this formula? What I'm doing here? I think you were about to say it. What do? I take a vector, I apply mu, I get a result. Then I apply mu again, then I apply mu again. Each time I normalize so I don't have a length going to infinity, but that's just a detail. If you look at the direction, I take a direction, I apply mu, and then I apply mu and apply mu.
Isn't it rotation?
Reduction? Rotation. This rotation? Not sure. But in more general than this, if you take any linear application, you take a vector and then you iterate like this, the linear application. Linear application has nice properties, it's cool and whatever. You take a vector and you iterate like this. And you take care that it doesn't grow to infinity because otherwise it's not fun. What do you get? An eigenvector? Anybody? An eigenvector. An eigenvector is vector such that you have, when you have matrix, you have mv equals lambda v for a scalar lambda. So we call lambda an eigenvalue and v an eigenvector in English.
I guess a root vector.
Well, I don't. Well, actually, what you will get if you do exactly this, you will get the one eigenvector for the largest lambda, or the lambda with the largest absolute value. The idea is that you remember you can diagonalize. So if you take the strongest eigenvalue, this is the direction that is favored. In linear algebra, if you have the eigenvector with the largest eigenvalue is the vector that attracts in some way the other. So if you apply this many, many times, you will get closer and closer to your eigenvector. And actually, this number will exactly be, well, you get this. For any vector v, no v, then I don't know, x, this tends towards, should divide by lambda, and it tends towards vector v.
What is a claim about eigenvectors?
So what I claim is that this is exactly the definition.
One more general for an arbitrary.
Okay, for an arbitrary, it's not exactly a claim. For an arbitrary matrix, you have several eigenvectors. Suppose, okay, forget about this for a moment. Suppose you write your matrix in a diagonal form, like you diagonalize your matrix. You know how to do this. So you have lambda 1, lambda 2, etc., lambda n, and zeros everywhere. And then this is in some specific base. When you diagonalize, you change the base, okay? So suppose, for instance, that lambda 1 is very, very big compared to the others. And so you have, of course, vectors v1, v2, and so on, vn. that corresponds to the different coordinates here. And if lambda 1 is very, very big, you take any vector, like this, and you perform this, you compute this limit. Actually, all the components here will tend to 0, except one, the first one is going to tend to 1. You see what I mean here? And so now this means that in the end, I will end up with 1, 0, 0, 0, 0. And what is the image of 1, 0, 0, 0, 0? It's exactly V1 expressed in this strange base. But if you come back to the normal base, you get V1. So if your matrix has an eigenvalue which is dominant, like it has a large absolute value compared to the others, this gives you, this grows towards the eigenvector that corresponds.
But is it true that for any network matrix we have n different eigen?
No, it's not true for each matrix, of course. That's what I initially said. Your matrix is nice enough. Not all matrices have different eigenvalues, but even they could be too close to each other and so on. You need actually even more. You need that this thing is primitive. So you need an eigenvalue greater than 1 and all the others smaller than 1. And like this, since they are smaller than 1, when you're going to take the power, this is going to grow to 0 and this is to grow to 1. Otherwise, you should be careful with normalization. So okay, I thought that you would be more familiar with this, sorry. But the idea is that when you take a linear transformation nice enough, you apply it many times, you will end up finding the eigenvector. This is a reason why in J-vectors.
Yes, we misheard that we're talking about matrices with the largest eigenvector is more than 1. And the rest
yes, okay, sorry. I try to be not too late for the break.
In general, it's not true.
No, it's not true. Actually, there is a whole theory about this, about primitive matrices and Piso substitutions that also like this. And it turns out that for many substitutions, like such this, if you take this matrix, you get a matrix that is nice. You might remember, well, for many interesting substitutions that show up, this is the case, and there is matrix. Sorry, I went a bit too fast because I didn't want to be late for the break, but it seems to be a fail. Sorry about that. So yeah, you should have, when I said large enough, this one should be more than 1, this one should be smaller than 1. But in general, really, you have a more general fact that if you have a vector and you multiply by a matrix, you will get somewhat attracted by the largest the eigenvector with the largest eigenvalue. And this is true in general. So it's not necessarily as strong as this, but you can give precise meaning to this, and this is why actually the eigenvectors are interesting things. Well, one of the reasons why, not only because it's practical for computation, they have a very nice formula with AMV equals lambda v, but also because if you iterate a matrix for a very long time, this is the vector to which you will get a bit attracted to if you don't have contradictory phenomena. And this remains true in the spirit, even if you don't have this very precise formal condition. Another takeaway. So that's it. So we connected the infinite words then with Hanoi towers, dynamical systems. Now we saw how to play with matrices. We could have done geometry. We could have done continuous fraction, but that's it. We'll have a break now. After
Where did we count the...
Sorry. You compute the eigenvector, the dominant eigenvector for this matrix, and you will find exactly alpha and 1 minus alpha, or the contrary. Sorry. I spent 5 minutes telling that this vector is cool, because if you compute it, that's what even you said. This has connection with Fibonacci numbers.
1.
Where? What, like this?
Alpha and 1. So, no.
It's 1.
It's
It-
n.
No, it's 1. It's 1. It's a very ugly one. No, my bad. Sorry, I think I wanted to put too much in only one slot. So, okay, after break, we have fun with the spheres for a few minutes, and then I can try to show you what I've done last year.